So what I mean by that is we have two vectors here. We have the boat's vector, which is traveling at 12 meters per second at an angle of 30 degrees west of north. And we have the current's vector, which is 6 meters per second due west. Now, in order to figure out the boat's velocity relative to the shore, we need to add these two vectors together. But the only way we can add vectors together is to add their components together. So we need to figure out the components. Now, components can be any combination of vectors that are at right angles to each other that make up the original vector. We said that yesterday. In order to make that work here, we need to choose a direction for our components that is the same for both vectors. So I'm going to draw a coordinate system for the boat. And I'm currently just operating on the boat. I saw a few of you attempting to do this. Great. Well, I'm going to make north and positive y the same direction. Now, just understand, I can choose any direction for my axes. I could have just as easily taken this and made them all this way and just said, this direction's positive y. I can pick whatever I want. I could have lined up the boat with the positive y direction if I wanted. All I need to do, though, is make sure I am consistent. Since my directions were given as north, south, east, and west, it makes sense to find my components relative to north, south, east, and west. So that's why I'm choosing to do it in this way. So east, positive x. The boat was 30 degrees west of north. So I'm going to draw the boat as an arrow, 30 degrees towards the west from north. Now, placing the boat's vector here, I'm going to assume is not terrible. It sometimes requires that you get used to the idea of what it means to say west of north. Start facing north, turn towards the west, 30 degrees. If you want to understand that, read it backwards. It works better that way. So I am now facing west of north because I was facing north and now I've turned to the west. So that's the nomenclature that we use. Get used to it. We'll see it for a day and then we won't see it anymore. In order to break this up into components, I'm going to choose to make my components aligned with the coordinate system. So my next step is to draw a triangle. And that triangle must be a right triangle that is aligned with my coordinate system. So I drew a triangle aligned with my coordinate system. Remember, the whole idea is to produce one-dimensional components that are aligned with each other. So I'm using the coordinate system as my alignment. It's a right triangle, and based on the way I've drawn it, this is the adjacent side, this is the opposite side, and this is the hypotenuse, and the hypotenuse is 12 meters per second. It doesn't matter what kind of vector this is. We're doing velocity vectors, but I could do displacement vectors, acceleration vectors, force vectors, momentum vectors. All vectors must be added together this way. However, you can only add vectors of the same type. So I can't add a position vector to a velocity vector, but I can add two velocity vectors together. I can add two acceleration vectors together. That's fine. Now I need to figure out the size of each component. But I noticed by just looking at this that my adjacent component is going to lie in the y direction and my opposite component is going to lie along the x direction. I'm going to tuck that away for a few minutes. And note that the best way to solve this is by using my trig. Sine of 30 degrees is opposite over 12. Cosine 30 degrees is adjacent over 12. And tangent of 30 degrees is opposite over adjacent. And truthfully, I would never write all of this out. This is purely for your benefit. But this tells me that opposite is equal to 6 meters per second. And adjacent is equal to, let's see, 12 times 0.866, 10.4 meters per second. I know that the tangent of 30 is 0.577. I can divide these two numbers to test to see if I've done my arithmetic correctly. You should try it. There's no reason to get these wrong. 6 divided by 10.4 is going to be 0.577, and that is the tangent of 30 degrees. There are lots of ways to check your work, and you should make sure you check your work. But now that I have that, I can use that to kind of complete a chart where I write in the boat's velocity in component form. It's traveling negative 6 meters per second, x hat, meaning in the x direction, plus 10.4 meters per second, y hat, which means in the y direction. This is the velocity of the boat in rectangular notation. It's the same information as before, except now it's giving me my values directly in the x and y direction. The current is along a cardinal direction. I could draw it if you're desperate to see it, but I don't feel like I need to. It's in the negative x direction. And I chose it this way because I wanted to do less work, not more. If I had chosen the current to be, something west of north, I would have had to do the same trig as I did for the boat. Does everybody understand? Great. I just made it so this would be faster. I knew what I needed to see in your work to understand whether you knew what to do or not. So I have now converted both vectors to rectangular. Step 1 is complete. Step 2 requires that I add like components together. Yep.
Are we not assuming that the boat at 12 meters a second is already being affected by the water?
It is being affected by the water, but that's only relative to the shore. The boat's compass is pointed at 30 degrees. The boat doesn't know that the water's moving. So I'm going to now add like components together. 10.4 plus 0 is 10.4 y hat. Negative 6 minus 6, negative 12 x hat. This is the velocity of the boat relative to the shore. I have added like components together. However, to get my answer, I need to convert this to polar. That generally involves me looking again at my components. I'm going to draw out a quick component diagram, meaning I'm going to draw a coordinate system, remind myself north and positive y, east and positive x, and show that I'm going to go negative 12 in the x direction, and positive 10.4 in the y direction. Notice that I drew these tip to tail. That's important. Some of you won't. Some of you will draw it looking like this and will make me absolutely crazy. So I don't know who is going to do this, and if it's you, I plan to put yours on the bulletin board. Don't do this, because I will. I'll put it right up there with big arrows on it.
Why would that be wrong, though?
Which angle is the right angle? Good, good, good. Now, when I solve this, which of these angles is the direction the boat's going? Neither. Right? The boat's not going that way. The boat's going that way. I need something that's going to tell me the direction the boat's going. This triangle will have the same qualities as the triangle I'm making, but without any reference. So generally, when you add vectors together graphically, which is what we're doing in this picture, is we're adding vectors together graphically. You add them so that they are tip to tail, like that. You add them in order. Because what this does is it tells you exactly where to expect your answer. I got those reversed, so hold on. My vector said to go 12 in the x direction and then 10.4 in the y direction. So I'm doing it just what it says, in order of what it says. That means that my actual velocity is the sum of those two. which is that angle. This is going to give me the angle the boat's actually traveling. Okay? All right. Now, this part of the process is very much the same as what you've already done. But again, I'm doing it longhand, so sine of my unknown angle equals, well, I'm going to label this one opposite, this one adjacent, and this one hypotenuse. Because based on my angle of focus, that's the names of those sides. So that's going to be opposite 10.4 over hypotenuse, don't know. Cosine of my unknown angle is going to be 12 over unknown. And tangent of my unknown angle is going to be 10.4 over 12. This example gives me one complete ratio. And because I have a completed ratio, I can figure out which angle goes with this ratio. In doing my trig, I found that the angle that goes with this ratio is the angle 40.9 degrees. I did 10.4 divided by 12 inverse tan, and that gave me the angle. Now, I am aware that you guys can jump on the Pythagorean theorem to figure out h, but I also want to point out that you can do trig here. This was 0.866. That's the ratio that I got when I divided 10.4 divided by 12. Yes, sir?
Since you're theta, wouldn't that be, we're doing north, west of north. Is that theta, so your angle, isn't that be from west to of north? If you're reading it backwards, you go.
My boat's traveling 15.9 meters per second, 41 degrees north of west. That's the answer. This is the boat's speed relative to the shore. This is the direction the boat is actually traveling relative to the shore. So, adding two vectors together. This is largely procedural, I hope you noticed. Meaning if you follow this procedure, you will likely get an answer. And the procedure isn't particularly complicated, but it is tedious. And you understand that making mistakes someplace is rough. Why did I choose 30 degrees here? Because I know some of you. And some of you have been trained to make your x component always related to cosine and your y component always related to sine. If I choose my reference for the angle that thwarts that, then you're going to get your components mixed up. And there's a few of you in the room when I walked around who had these wrong. That's because you're complacent. You're assuming your reference is always the same, and the reference doesn't always have to be the same. Now, you can change your reference, that's fine. But if you're thoughtful enough to change your reference, you're thoughtful enough to pick up on why cosine and sine are not always x and y. All right? I would call this a level 1 problem. It's simple. You're just adding two things together. It's complicated in that there's a lot to do here, but you really are just adding two things together. Vector addition is harder than just normal algebraic addition. But let's see if you can do what I actually like you to do. All right. All right, here we go. I don't know what direction the plane is going. However, I know what direction the runway is, and I know what direction the wind is. So I'm going to start by just giving myself some reference. All right, so there's the runway. I'm told the wind is blowing 25 degrees south of east. So here's my vector for the wind. I'm not drawing necessarily anything in to scale. I just want to be able to see it. If I want the plane to land by traveling down the runway, then I think the velocity of the plane is going to have to point that way, so that the wind will push the plane back on course. So I don't know what direction that is, but I'm going to call that direction theta for now, for lack of a better thing to do. The wind is blowing to the south, southeast. So I'm going to fly into the northwest, so that the combination of those will likely keep me traveling down the runway. Now that's the first thing you have to do, is you have to come up with a plan. And that's my plan. And thank you for not stopping. That means you all understand that thoroughly. So 150 is the speed of the plane. I'm going to do the same things we talked about before. I'm going to take the plane and the wind and convert them from polar to rectangular. The plane is 150 degrees at some angle, I don't know. The wind is 50 meters per second. I'm sorry, I said degrees here, but I meant meters per second. And is at an angle of 25 degrees, looks like south of east. So I'll need to come up with the x components and the y components of each. West of north. It's not arbitrary. I know it's got to be in the second quadrant. So there. But not knowing what it is, reference feels arbitrary anyways, but okay. Now, let's start with the wind. That one I know we can work out. I'm going to set up a couple of components for it. I know that I'm going to draw a component along the x direction and a component in the y direction. I'll make this my adjacent side and my opposite side. This is my hypotenuse. So I'm not writing everything out anymore. My assumption is that you guys are all over that. So let's see, 50 times, I'm going to get 21.1 meters per second that way. And 45.3 meters per second that way. So those are my two components for the wind. You should write out all the sine and cosine if you have to. I don't. So the adjacent side is in the x direction. That's the positive x direction. So positive 45.3 x hat. And the 21.1 is in the negative y direction. So minus 21.1 y hat. Now let's go to my plane. If I was to draw my component vectors out, I would draw my components to look like this. And this would be my adjacent side, and this would be my opposite side. I don't have the angle, so my adjacent side is just 150 cosine theta. My opposite side is 150 sine theta. So I don't have the angle, but I can still write an expression for each of these two sides. My opposite side points to the negative x direction. So negative 150 sine theta x hat. Yep.
Can you assume that the sum of the x hat and the plane and the x hat for the wind will be 0?
I can. It's not there yet. So my adjacent side is 150 cosine theta. Those are my two components. I don't know what either of them really is because I don't know what theta is. But as it was just pointed out, there's more information to bring to bear here. I've successfully converted my vectors into rectangular. And now I'm going to add like components together. But I know that my x component has to zero out. The amount of the plane's velocity in the x direction has to be 0, so the plane is only traveling in the y direction. That requires a little bit of problem solving, but I know that that has to be the result. If that's not the result, the plane is going to be drifting in the x direction and it's not going to stay on the runway. Now that alone is a direction to solve the problem. Because if I look, I'll notice that negative 150 sine theta plus 45.3 has to equal 0. This has to be true for the plane to be flying due north. Once I know that, I can figure out what my angle is. And it looks like my angle is going to be, let's see, 45.3 divided by my 150. I have 17.6 degrees. So if I fly 17.6 degrees west of north, my plane should travel directly along the runway. It also means the plane is going to have to touch down, not facing down the runway. Anybody who's been on a plane before knows that that happens all the time. Especially here in Florida, where all of our runways in Tampa International all face east and west. North and south. So if there's a cross breeze, and there always is, the planes always have to face into the wind in order to land. This doesn't tell us everything. It just tells us the angle the plane has to face. You could figure out how fast the plane is going down the runway if you'd like. Plug theta in, get your y components. That's how fast the plane is going down the runway. So not a bad thing to ask, and I probably would find the ground speed of the plane as it hits the ground. But I think that we've kind of figured this problem out. Or at least I've explained it to you, and nobody has stopped me, so that's good. Yep. I'm not going to recognize this any longer, guys, just so you know.
But what about, backwards, does the wind reduce the plane's forward momentum at all?
It reduces its forward ground speed, sure. That would be the answer of finding out what this component is. I'm not sure what you're interested in knowing here, but you could find this out. Do so. 150 cosine 17.6 minus 21.1. So the plane is flying 150 meters per second relative to the air. It will land on the ground traveling 122 meters per second in the y direction. And it's because the wind is slowing down its progress along the ground, which is why this is less than the 150 of the plane. Okay so far?
Yeah, I understand everything mathematically. I'm just trying to wrap my head around it.
Okay. I'm not sure I can do the head wrapping. But I will state that there are conditions in which planes can't land. Right? You can probably imagine that if the plane is facing too far into one direction in order to land along a runway, that would be pretty dangerous for the plane, wouldn't it? Because what is not being stated here is that in order for the plane to actually land on the runway, it has to face 17 degrees away from the runway. Generally, what pilots do is they touch the back wheels down first. And before they touch the nose of the plane down, they allow the fact that the plane is now touching the ground as a way of torquing the nose over and then laying the nose down in front of the plane as opposed to the side of the runway. Should that angle be too great, then that's an unsafe condition for landing, and they would route planes to a different airport. Now, some airports, not Tampa International, have runways in opposing directions just for this purpose. So if you look at runways from the sky, you'll notice several of them have cross runways that run at an angle to their main runways, purposefully for when there are conditions where the main runways can't be used. And also they choose runway directions based on what will be most economical for flights. So if you look at Tampa International, most of our flights tend to leave towards the north in the morning and land with planes going towards the south in the afternoon. It kind of makes sense, since in the morning most planes are going into the continental US. So rather than have them fly south and use all that fuel to turn around, they just fly them north and get them the heck out of the city. They don't always do that, but often they do. When wind conditions don't prevail, they have to reroute the planes. It happens all the time. Planes have a certain speed, though, that they have to be under in order to fall out of the sky. But they have to be fast enough that they don't fall out of the sky too fast. There's a variety of things that are involved with dealing with planes' motion. But it is quite possible, to consider other situations here. And I have been incredibly surprised by the number of students who find this next exercise to be challenging. You stand on the side of the road next to a truck. Truck's traveling towards you at 10 meters per second. How fast is the truck going relative to you? 10 meters per second. That's right. It's covering 10 meters every second. You are not moving relative to the ground, so you see the truck's speed as the truck sees the speed. Fair enough? You have a friend in the back of the truck. Friend in the back of the truck is looking at you. How fast are you going relative to your friend? Sure, negative 10 meters per second. Right, he's traveling the other way. Now, if the truck weren't moving and you had a ball and you throw the ball at your friend and the ball leaves your hand at 5 meters per second, how fast is the ball traveling relative to your friend? 5 meters per second. He's going to catch the ball. He would measure the ball traveling 5 meters per second. If the truck were moving forwards at 10 meters per second and you throw the ball forwards at 5 meters per second, how fast is the ball traveling relative to your friend? 15 meters per second, sure. The ball leaves the truck at a speed of 5 meters per second, but the truck is moving relative to the ground. So the combined speed of the ball and the truck would be 15 for the person catching the ball. Does that make sense? If you didn't throw the ball and just dropped the ball, would the ball fall straight down and hit the ground here? No, it would hit the ground over here, right? Because the ball is moving forwards at 10 meters per second. The ball becomes a projectile and will travel as a projectile would until it reaches the ground. In fact, if you just drop the ball, he will measure the ball leaving your hand at 10 meters per second because it was with you in the truck, traveling at 10 meters per second. Is it too much of a challenge to predict what would happen should you throw the ball backwards? If you throw the ball this way at 5 meters per second, is the ball traveling forwards or backwards relative to the ground? Forwards. Your friend measures the ball traveling what speed? 5 meters per second. What direction? Forwards. Yeah. Not hard, I don't think. It might be more difficult and I don't think it is, but it might be more difficult if we asked about the friend throwing the ball. What if the friend throws the ball at 5 meters per second towards you? How fast is the ball traveling when you catch it? 15 meters per second, sure. He's reducing how long it takes the ball to make it to you because he's throwing the ball at you at 5 meters per second. If the truck wasn't moving, how fast would you measure the ball speed? 5 meters per second. And if he just held the ball and the truck were moving at 10 meters per second, how fast would the ball be traveling relative to you?
10 meters.
Sure. All that okay? This is one-dimensional relative velocity questions. I don't believe they're particularly hard. Mythbusters took this to the extreme by trying to travel at 50 miles an hour and fire a ball backwards at 50 miles an hour to see if the ball would just fall out of the cannon. It does. I'll show you the video tomorrow. It's not particularly great, but if you need to see it, I can show you. But you could look it up just as easily. You understand the rules of YouTube.